Hello, hello, hi everyone. We're gonna go ahead and wrap up the last lecture of this week. Let's get started. So these last two sections are kind of just they're kind of just the more practice problems, but they're specifically delving in how not hard, but just how weird these integrations look. So for instance, when we're doing exponential, we know the exponential is just the exponential, right? Because its derivative is the exponential. The integral should also be the exponential. However, what if the integral is presented with something inside? And like the chain rule property, we need to do something about that. Well, we can set up to be u to be gx, and then du to be g prime of x dx. And that would turn this into an integral of k times eu du. And that would result in k e to the power u, and then you plug in back u. So hopefully that step is easy to see. Similarly for over here, you know that the integral of an ln puts something on the bottom. So you sub u to be gx, and du would be g prime of x dx. So it would turn into integral of from k over c, and then 1 over g of, or I'm sorry, g, u, and du. And then that would let you clock that that's, a log function. You can't use the power on that because you'll get divided by 0. And you would get that expression there after plugging in back u. So it's technically straightforward, but obviously the idea of using substitution for these is a bit newer. So let's go ahead and start here. We see that this integral would be a lot easier if e was to the power of just a singular variable in that 3x. So I'm going to write it as u is equal to 3x. But then I need to make sure my derivative works out. So derivative of that is 3 and then dx. Well, here I don't have a 3, and I could be, technical and factor out 5 out of 3, but really I rather just rewrite it to where it doesn't need 3. It just needs dx. So divide both sides by 3, and then you'll have 1 over 3 du is equal to dx. And then, here, let's use different colors for this. You plug in these guys. So we see here that x will take up that, and here 3x will take up this. So you're left with the integral of 5e to the u du, and then that 1 over 3. And then technically you can even take out the 5, so 5 over 3 integral eu du. And we get 5 over 3 eu, and then plus c. And then from here you plug in back u. 5 over 3 e, and then 3x plus c. And notice how that basically copied what happened here. The only sort of caveat that you have to deal with is, well, what did that g of x imply? Because technically that g of x wasn't there, right? G of x was 3, and 3 wasn't there. So you had to do a little manipulation, but it wasn't too much manipulation. And you get the answer. All right, let's keep going. Again, this problem would be easier if that was just a variable, so 2x, and then du would just be 2dx. And then solving for dx by dividing by 2, and then I'm just going to rewrite it like this side by side. Again, here, that's going to be the u, and you're just replacing dx, and you'll have negative 1/2 integral of EU du. And you have negative 1/2 EU plus C, and then you plug in back EU, 1/2 E to X plus C. And that's the answer here. I'm just going to briefly just glance at my solutions just to make sure that I'm not forgetting something super trivial, because right now, yeah, okay, cool. Just double checking. You never know. We're all human. We're all prone to mistakes. Okay, let's keep it going. Okay, we got this one. This one says, has a similar e to the x idea. So u will be 3x squared. And we see that this integral in some ways appears as a product. I mean, this derivative, excuse me, appears as a product. So du is equal to 6x and then dx. So we see here that we can replace dx, we can replace x, but we can't replace 6. We have to make it appear. So you can either manipulate here. I'm just going to choose out to divide out the 2. So we have 1/2 du is equal to 3x dx. So then with that, I'm just going to go ahead and replace the 3x and the dx. And here replace 3x squared. So you have negative 1/2 integral from 0 to 2, and then EU du. Wait, let me check that. Those were, I didn't skip in depth. Okay, cool. Now the gimmick here is that we're jumping to a definite integral. So I don't really have to write the plus c anymore, but I do need to keep up the notations. For example, we're not doing u, we're doing 3x squared. And we're doing it from 2 to 0, 2 to 0. So in that case, you'll have a final answer of E12 and then minus 1. Because e to the 0 is just 1. All right, pretty good so far. The only thing is that maybe you didn't factor out the 1/2 and you left it in there. You still would have gotten something very similar. You just would have gotten this times this and then this times this. It became positive. Okay, happening again, where it seems that this derivative in some ways appears here. You got 3x squared dx. The only thing that doesn't appear is the 3, so we're going to take it out. 1/3 du is equal to x squared dx. Let's replace x to the power of 3 with u. Let's replace x squared and dx with 1/3 du. So I have 1/3. I'm just going to let that escape already. I have EU du. We know that's just going to become EU 1 to 0. Again, we're doing definite integrals, so we don't have to include the plus c anymore. And then we have to replace a u back for what it was in terms of x. E to the x to the power of 3. And from here you have 1/3 with e minus 1. Okay. All right. Now the problem has slightly shifted into logs. So it would be more recognizable if this whole bottom thing was just a single variable. So let's just make that adjustment, x plus 1. In that case, though, du is just dx. The constant disappeared, and derivative of x is just 1. So you do have everything for this. You have the bottom, which will just turn into u. And you have this guy, which should just literally swap the dx for a du. So you have, I'm going to put the -3 on the outside, 1 to 3. And you have 1 over u du, which is just ln of u from 3 to 1, and then you have to plug in back u. Ln of x plus 1, 3 to 1. And then from here you can get a calculator approximation, sure, but I rather just write it out in as an exact answer. Ln of 3 plus 1, 4, minus ln of x plus 1 when x is 1. So minus ln of 2. All right, let's keep going. Seems we're going to have a similar pattern here. X minus 3 du is dx. Place this whole bottom part with u, and just swap out the du for a d. I mean the dx for a du. 2 integral from 4 to 6 of 1 over u du. That's going to be ln of u again from 6 to 4. But then we have to plug in because these are for x technically, so ln of x minus 3. 6 to 4. Then you get ln of 3 minus ln of 1, which you can technically, ln 1's one of the only ones that we can for sure simplify because it's going to be 0. So you're just left with 2 ln of 3. All right, let's go in here. We have the convenience of making this whole thing one variable and its derivative appearing more or less alongside it. The only exception is with that 3, so we need to take out that 3. So 1 over 3 du is equal to x squared dx. Then from here we can go ahead and replace this whole bottom part, and then replace this and this with a 1 over 3 du. 1 over 3, going from 2 to 4, of 1 over u du. We know that's just going to be 1 over 3 ln of u, 4 to 2, and then we plug u back in. X to the power of 3 minus 1. Okay, then from here, 4 to the power of 3, which I believe is 64. Yeah. And then 64 minus 1 is 63. And then 1 to the power of 3 minus 1, which is ln, wait, 1, 2, excuse me, 2. 2 to the power of 3 is 8, and minus 1, 7. All right, last one. So it does seem again we get to take advantage of the trick where u is x squared plus 1 and du is 2x dx. The only thing that doesn't appear is the 2, but we can easily remove that. Place that bottom part. I place only here and here. 1 over 2, integral from 1 to 3, 1 over u du. 1 over 2, ln of u, 3 and 1. Replace u with what it originally was, ln of x squared plus 1, 3 to 1. Okay, then from here, you should get ln of 3 squared is 9, and then plus 1, 10, minus ln of 1 squared, which is 1 plus 1, so 2. All right. pretty straightforward for all of these. The only thing I would say is that I was really consistent about taking out the constant, so your answer would only look uh different if you didn't. And if you did, well then you just distribute the constant in front of all these pairings. Except for this one. This one probably looks the same because that ln of 1 would have disappeared. So like for example, this 1 over or e over 3 minus 1 over 3, stuff like that. So just keep that in mind in case, or if you wrote as one big fraction, if all those answers are equivalent and like none would get like points off on the exam. All right, let's move on to another set of problems. Let's do this color. Okay, so integrals resulting in inverse trig functions. So recall the idea of the derivative of trig function, right? It's this sort of weird square root pattern where that x was always squared. This is a very unique pattern. So if you're to see a pattern of similar ideas, then you could go ahead and argue that it's the same thing. The only new thing that we're including this time around is the change from 1. We're going to go ahead and include the idea that x can be presented with a constant. The constant initially appears as a division. So keep that in mind because I'm not going to necessarily trick you crazy with these kind of problems, but it can come up. So, because to be honest, I'm almost done writing the test and I literally just haven't finished this part. So I still actually, as of this moment live, haven't decided how to ask you a question like this, but I'm debating where to give you a 1 or like an actual A, but we'll see. I can't promise anything. Alright, so let's go ahead and record this. From here, you see that this whole expression, right, is very eerily similar to one of our inverse trig functions. Now, technically speaking, there is 2 trig functions it could be. It could be the sine or the cosine. It depends on the negative value provided here. So, depending on what negative value, it will turn to sine or cosine respectively. However, we see here that we have a positive value. So if we have a positive value presented to us, then we can go ahead and just use the sine or the sine inverse. Now, the only thing is that we need to identify what x is and what a is. Well, x is just x. That hasn't changed. And then a is not 4. A squared is 4. But a is what then? 2. So that means this whole thing, here I did this a little bit out of order, my mistake, is if we take out the 3, 1 over the square root of 4 minus x squared, we can get out, excuse me, this to be 3 sine inverse of x over 2, and then plus c. So that's pretty much it. We're just kind of copying and pasting the formula at that point. The only one where that A becomes a bit more important is the arctan, but you'll see it pop up, so we should be good. All right, over here, I'm going to take out the 4. And I see here, though, if a squared is 16, then a must be 4. So the answer, oh, I forgot dx. I forgot dx here. So the answer should be 4 times sine inverse of x over 4 and plus c. Over here, we no longer have that pattern of square root. We have the pattern of it being over. So we can go ahead and just rewrite it a little bit, but we'll see that we have an arctangent or tangent inverse problem. But remember, a now is a constant in front and inside of the tangent. So if a squared is 16, then a must be 4. So you'll get 5 times 1 over 4 tangent inverse of x over 4 and plus c. The only real adjustment I can make to this is just to make that prettier. 5 over 4 tangent inverse of x over 4 plus c. Over here, we got one more thing, 3. 1 over 9 plus x squared dx. If a squared is 9, then a must be 3. So you get 3, or I'm already going to write divided by 3 tangent inverse of x over 3 plus c. And then here, that we know that just simplifies to 1. So the answer has a further simplification, tangent inverse of x over 3 plus c. And that's pretty much it. So that's going to be your answer for all of these guys. The only thing I will say is that the homework is going to challenge you a little bit in wrapping all these lessons up. Because I didn't do those examples where there's trig and there's log combined. So I'm going to leave that up to you to do that. Okay? So that's going to wrap up today's video. Let me know if you guys have any other questions, and I'm going to see you all in the group work video. Bye-bye.